Welcome to this episode of the APL Quest. See APL Wiki for details. Today's quest is generating an identity matrix of order n. Very simple task, but a lot of interesting ways we can do this. Let's get started with some serious solutions and then look at some more fun, innovative solutions after that. So, the first thing we can do is that we have a number n. Let's, for argument's sake, say that n is 5. And we want to make a matrix that is 5 by 5. So we can concatenate n to itself, giving us 5 by 5. Next up, we can generate all the indices of an array of shape 5, 5. And we can take these indices and look at where the horizontal and vertical index are the same by comparing each. And this gives us our identity matrix. However, we can do this in a simpler way. We only need to generate the indices until n, and then make an inequality table using the outer product and the selfie or commute operator to use the same indices on both sides of the equality. And in fact, this is our simplest solution. So just the outer product selfie on the indices. It isn't a very efficient solution, however, because we are comparing a lot of numbers that we have generated when we actually know where the ones are going to be in advance. So what we can do is we can start off by creating an empty matrix of zeros. So we take n and use that twice to reshape 0. This gives us a big empty vector like this, empty matrix like this. No, it's not empty. It's a big 0 matrix like this. Then we can use dyadic transpose, which selects the can collapse dimensions so that we get diagonals. We can illustrate this by saying 5, 5 reshape iota 25. And then we can use dyadic transpose, mapping both dimensions to a single dimension, and that gives us the compromise between them diagonal. So now we can use this with a selective assignment. We say 1, 1 transpose of S gets 1, and the 1 then gets distributed over the entire S. And now S has been updated to become an identity matrix. We can put this into a function as S gets omega omega reshape 0, and then the diagonal of S gets 1, and then return that S. And we can now give it the argument 5. Fine. This is verbose, but it works. It doesn't have the best performance necessarily. And it's a bit awkward because we have to have this middle statement where we update S before we then return S. We can also use the @ operator to do something similar. We can start off by generating all the indices that need to be set to 1. How can we do this? Well, if we start with this iota n in our case, then we know that it is the elements of position 1, 1, 2, 2, 3, 3, 4, 4 that need to be set to 1. So what we can do is we concatenate to itself each one of them, and these are the indices that we need to set to 1. And then we can use this setting 1 at those indices in the array that is nn reshape 0. And that will give us our identity matrix. We could also use these indices in a different way. Namely, we could say, give me a Boolean matrix that has 1s in those positions. So where are all the 1s in a Boolean matrix is monadic iota underbar. And the inverse, we can use power -1 on that. And that gives us an identity matrix as well. there are even more things that we could do along these lines. Instead of using a matrix, we can use a vector. And the way we can do that is by observing that this is kind of an encoding of in a special radix. So we want ones, and when we do things like that, we need to set quad IO to 0, otherwise it becomes too complicated. So what we can do is we have the indices iota n here, and then we can multiply those by n, and so this corresponds to let's see, number 0 is this element, and number 5 is this element, and number 10 is this element in Ravel order. However, we need to offset 1 for each one. So if you take these indices and add them to this, that gives us in Ravel order the diagonal. We can actually see this. If we say 5, 5, reshape iota 25, we can see that 0, 6, 12, 18, 24, those are the diagonals. And once we have those, we can then use the add operator as before. So we can set ones at that in a vector, which is 0 reshaped to the shape of n squared. And this is our flattened identity matrix. Now we can take the proper shape and reshape it, and we get our identity matrix. Let's change back to quad IO 1, index origin 1, and then actually do some the best performing solutions. And that we can observe, similar to what we've done now, we can see that there are exactly n zeros unto the next one, and then again n zeros to the next one. So what we can do is we can begin with a 1, followed by n zeros, and then we can reshape that cyclically into our full shape. I'm going to use n here. And this is almost as good as it gets. There's one problem. For a very large n, we create a Boolean vector of all zeros, and then by inserting one at the beginning, it gives us suboptimal performance because we need to copy this entire array one step over, shifting everything by 1 bit to insert that leading bit. How can we avoid that? Well, we can use overtake. So if we say n take of 1, it pads with additional zeros at the end. And the only thing we need to do here is really adding n plus 1. And this gives us that full row. And now we can reshape into that shape. So this is going to be the best it gets. We can put this into a function as omega omega reshape omega plus 1 take 1. We can also make this into a tacit form, and we can play some tricks there. So let's split up the problem. Omega omega, that is the self-concatenation of the argument. Then we reshape that, and then we want the argument plus 1, so we can tie or bind a 1 to plus, making it a monadic function, so that's an increment function. And we use that to take from, well, we need a 1 here, but we can't have 1 at the end of a tacit function because it's a constant, not a function. We can transform it into a function using the constant operator. So we can try this as well, and that works. And then for a little bit of trickery, we can actually avoid this construct of one constant by observing that the sign of 5 is 1. And the problem was that we needed on the right hand to have a function, not a constant. So this is a function applied to any number that's relevant, and we get 1. If we want a 0 by 0, it doesn't matter that the sign of 0 is 0. It will still work because it becomes an empty array. So it doesn't matter that we are taking from 0 there. So we can do this. We can say I5 like this. Another possibility is observing that how many elements are there in a single number. There's only 1, and that applies even to 0. So we can do that as well. So this is a this is the fastest solution that we're going to get. This is a proper solution. Whether you want to use a tacit form or the default, it should be about the same performance. Now onto some more fun and innovative solutions that we could do. And remember again that we needed a single one followed by n zeros. And we can actually do that using expand. So if we have a 1 representing that we want 1, 1, and then we have negative n representing n fill elements, we can use that with the expand function on a single one to get the same thing. And then we can reshape that to our identity matrix. And we can write this in a tacit form. So this is, again, the self-concatenation reshapes 1 expanded by 1 followed by the negation. And it works for 0 as well. What happens in the 0 case is negation of 0 is 0, so we get 1, 0. That means we expand 1 as a single 1 with no fill elements, reshape that to 0, 0, and we have an empty numeric matrix. So that works as well. Here's one that almost always works. Like, there is an astronomically small probability that it won't work, but it is rather fun. Let's say we have a matrix of random numbers. So with the 0 as argument, question mark gives us random floats between 0 and 1. So they won't be 0, they won't be 1. And it's exceedingly unlikely that we'll have duplicates here, of course. Now, if this is a matrix, then there must exist a matrix such that M, and multiplication here means matrix multiplication. We can write that as plus dot times. Will give us, but in traditional mathematics just the times, will give us the matrix itself, and that is the identity matrix. Now, if we move things around in this equation, we'll find that dividing the matrix by itself should give us the identity matrix, and indeed that is so. So we can do M matrix divide with M, and that gives us an identity matrix. And we can write the whole thing as matrix division selfie on the random numbers of the self-concatenation of 0. So here's a constant 0 again. We can try this, and it works. Similar to what we did with sine and tally to get a 1, there's also a function which for a single number, a scalar, gives 0, and that is the depth function. So the depth of a single number, a scalar, simple scalar, is 0. So we can go up and amend our function to this very obscure looking thing, which works just fine and is very, very inefficient because APL will have to solve an equation system every time we generate an identity matrix. But hey, it's fun, right? Here's another one which is very, very inefficient. Let's think about it. We've got the indices up to n. If we subtract these from n itself, that gives us descending powers from 4 down to 0. Raise 2 to the power of that, and we've got descending powers of 2. And now if we go up and look in our identity matrix, then we can see that the first column is 16 spelled out in binary, and the second column is 8 spelled out in binary, and 4 and 2 and 1. So this means that if we represent all these numbers in a in base 2, then we would get the identity matrix. So we could do something like this, which also sizes, but we already know that we want n bits. So we can say n reshape 2, encode on that, and that works as well. And then we can make the whole thing tacit by saying that it is the reshape of 2. So this is a monetic function which reshapes 2, encodes 2 to the power of the argument minus iota on the argument. So this works just fine. But again, very inefficient doing base conversions when we just want to create an identity matrix. But fun, it's fun. Okay, a little bit more and of fun. We can generate the negative indices, and then we can overtake like we did before on a1. So each one of these will be used to take from a1. So it takes from the rear padding with zeros at the front. Oops, that was too much when you're missing an each there. There we go. And now we just need to stack them up on top of each other, and there are various ways we could do that. We can mix, or we could use the rank operator. So we want to pair these up. Oh, we need to do take. Pair these up with 1, and then it mixes everything together, so that works as well. And now we can put all of this together to create a tacit function. So we have the negation of iota, take rank 0 on, remember how to get a 1 without using the literal one. We could use tally, for example. So this should work as well. And here's our identity matrix in a rather roundabout way. Another thing we can use is scan. So we can get normally prefixes of a vector like this. If we, instead of concatenate, so this is a cumulative concatenation, we do a cumulative swapped concatenation, then we get these reversed prefixes instead. Okay, so if we can have a way to get reversed prefixes, and we have a way to get 1 followed by a bunch of zeros, then these gives us our rows, and we just need to mix. So we can write this as a function, the concatenation swapped scan of the take of 1. So this is an n take 1, and then we mix that. Then we just need to put a top here, so we have 2 functions after each other. And here we got our identity function in a very roundabout manner. But lots of fun again. Now let's move over to the key operator, which we can also use for this. So we can generate our indices like this, and then we can ask the key operator what are the indices. So let's put it like this for now. So this is saying index 1 is found, or the number 1 is found at position 1. The number 2 is found at position 2 only. Number 3 is found at position 3. That means the alpha here is 1 and omega is 1. Alpha is 2, omega is 2, and so on. Now we can use take here, and that gives us these vectors, and we can see where we're going with this. We can then reverse this, and now we just have the problem of the sign. So we can take the sign of all of this, and we need to stack them on top of each other as well. So we could mix it like this, but there's a better way. By not enclosing them, we already get the mix for free. And now we just need to get the sign here. And then we can make this tacit because it fits very nicely. It is the reversal on top of the taking of these 2 arguments. And that gives us our identity matrix. It's not quite a function yet, but we can make it so by combining the key with the indices. And now we have our identity matrix generator in a totally obscure way that nobody will be able to understand. Don't do this in production code. Let's make it worse. Let's start again with this construct. And here we are only interested in the right argument. So that gives us these vectors of indices, 1 by itself, 2 by itself, 3 by itself, 4 by itself, 5 by itself. And remember, we used the iota underbar, the where inverse, to generate a Boolean array that has ones in those positions. There's only one position in each one, but we can still do this. So this gives us these vectors, and yes, you recognize this. Remove the enclosure, and we've got our identity matrix. And we can combine this, we can make the operand tacit simply by saying that it's this where inverse on top of the right argument. We have to have that because there's a left argument as well. So this is our function. And that works. Again, don't do this in production code, but it sure is fun to look at. And then somebody asked during the live chat event if we can't use complex numbers for this. And of course we can use complex numbers for this. Okay, let's get started. So we have these indices, and let's make a table of complex numbers. So we do the outer product of the real part plus the imaginary part. So we multiply the imaginary unit with these indices. Oops, there shouldn't be n here. It should be that. And that gives us a complex number table. So this is 1 plus 1i, 2 plus 1 plus 2i, 1 plus 3i, next row 2 plus 1i, and so on. And now what we need to do is we want to find out the ones that are down the diagonal. And both actually down diagonal, we can kind of see the angle of them. But it also happens to be that in a complex plane, these will have an angle, and also known as the argument, which is 45 degrees or a quarter of pi. So we can ask for the argument of that, and we can see that going down the diagonal, they all have that 0.785 and so on. Now we can multiply that by, or rather, divide pi by that. So the same thing as taking the reciprocal and multiplying by pi. And then we can see that gives 4. And now we can say, where is 4 equal to that? And that gives us our identity matrix. So this is our full function would be we could either do iota omega here, or we could just use omega and put iota outside that as an top, and we've got our identity matrix producing function here in a terrible way using complex numbers. And as if that wasn't enough, let's go in and modify this a bit. So starting again from here with our table of complex numbers, we can also ask what is the absolute value or the magnitude of these numbers. And since they are on the 45-degree angle, that means the horizontal and vertical parts in this right angle triangle are equal to each other. That means that the diagonal's length has to be a multiple of the square root of 2. So we can ask, what is the divisional remainder when these numbers are divided by the square root of 2? And if there is no remainder, then we are on the diagonal. So we can compare this with 0, and we get our identity matrix using complex numbers. That's enough fun. And what you should do, of course, is use the solution where we take the argument twice, reshape with 1 plus the argument take over of 1, or you can use the tacit version where it's a self-concatenation of the reshape of the incremented number take of 1 or as a constant, or you can use the sign or the tally if you really want to go there. But these would be the industrial strength versions. You can also go up and, if you don't like parentheses, like I personally don't do, then you can swap the arguments of this take as well. That's perfectly acceptable as well. Thank you for watching.